my name is Matt Spencer. I'm a software architect with ARM, and I'm here to talk to you about the journey from cloud native to car native. So first of all, a little introduction to me. As I said, my name is Matt Spencer. I'm a software architect in ARM's Automotive and IoT business line. I'm responsible for the software architecture I'm going to talk to you today about. I've been an embedded software engineer for over 20 years, and outside of work, I'm a open source software enthusiast. I love rugby. I am a coach in a local rugby team, a qualified referee, and still play touch whenever I can. Touch rugby, that is. Okay, so that's me. Firstly, I wanted to explain what cloud native means. In my experience, you can talk to 10 people, and those 10 people will give you a different answer. So I put here the official terminology from the CNCF, who are the owners and curators of the cloud native standards. I'm not going to read this out to you. You can read offline if you desire, but basically, cloud native in its essence doesn't mandate that we have to do anything in the cloud. It is more a bringing together of best of breed software methodologies, testing, CI/CD, and workflows that, when brought together, enable large, complex software systems to be built and deployed at scale with a high degree of manageability and quality. Breaking that down a little bit further, cloud native brings into scope something that they call a DevOps process, which is the bringing together of the development workflows and the operation workflows into a continual release and improvement cycle. So on the development side, you can see here we go through the planning, the creation, the verifying, and the packaging. So this is how we plan what we're going to build. We then build it, we verify or test it, we package, and then we go into the operations side where we plan for the release, we deploy to the target system, and then importantly, this stage of monitoring. So we have processes in place for verifying in situ that it's doing what it's supposed to be doing, and the output of that monitoring process can feed back into the planning cycle for the next step. And this cycle continues indefinitely, and this is how we get our continual improvement, continual integration, and continual deployment of these large, complex software systems. Cloud Native is also focused on standards, and I've pulled a few of them out here and the standards bodies that own them. So at the top level here, we have OCI, which is the Open Container Initiative. And this holds standards around container runtimes, container image specifications, and the container deployment specification that's not listed here. And that expresses to systems how a container is packaged, what the system requirements for running that package containers are, and how that package container gets deployed to that end system. Within the CNCF, the Cloud Native Compute Foundation, we have other standards, things like CRIs, CNIs, CSI, which cover things like CRI is the container runtime interface, which is the contract between the orchestrator and the container runtime. So that describes how the orchestrator configures and deploys the containers and how it monitors the health of those running workloads. CNI covers networking, overlay networking, firewall configurations, and the like. CSI for storage. And I bring into scope Parsec here as well. This is some code that ARM and our partners have worked on and donated into the CNCF that covers standardization of security aspects and makes use of, from ARM's perspective, ARM's PSA APIs. So adoption of these standards across the board helps to improve the quality, the deployability, the maintainability of these large systems. So that's what cloud native is. So I want to have a look now about the market trends towards cloud native in the automotive domain. So at ARM, we've been talking to a number of OEMs and tier ones within the automotive domain, and they've all expressed to us this desire to move towards a more centralized compute system in a transition towards a software-defined vehicle. And that software-defined vehicle is where you take a system today that has multiple discrete compute modules and consolidate them into a single central compute. And there'll be other talks at Dev Summit that are explaining this much better. But from a software perspective, what it means is, on the left-hand side here, we have the old style of monolithic application. So this would be a large, complex bit of software that has been built and tested, brought together, and deployed to the end system. This doesn't really express the cloud native view very well, because cloud native is all about delivering microservices. It's about breaking components down. So as we are moving towards that software-defined future, we're seeing us move more towards the right here, where we bring into scope the operating system with many microservices that are now running on top. So that's that monolithic system that's been decomposed into smaller functional blocks that are easier to test and validate. And we can make use then of container runtimes and orchestrators to control the deployment of those microservices. And you can start to see how the things like the CNI enable us to configure the networking infrastructure to allow these microservices to talk to each other. Moving even further, we can see here that we've got microservices now based on mixed criticality requirements of the automotive space. So we have real-time and functional safety requirements that come into space. And this is where we want to get to. We want to get to this endpoint of fully heterogeneous mixed critical workloads being deployed in a safe and consistent fashion. But that move from the infrastructure space to the car, there are things that are missing from the cloud native standards, and I'll run through these quickly. So one is software portability. Cloud native has a view of write once, run everywhere, and that is easy to understand when you have a single compute architecture or few compute architectures with little reliance on external I/O and accelerators, and there's no real need for that in the infrastructure space for the majority of workloads. So we need to understand how in the car we can get consistent access to ML accelerators, GPU, the I/O interfaces that are expressed. We also need to understand what mixed criticality means in a cloud native space. So that's how we express to the orchestrator the real-time and functional safety requirements of the workloads that we're deploying. And the seamless deployability that talks about how we need to have that execution environment parity. And this means that if I'm deploying to the car or into the cloud for testing and validation, we need to be able to make sure that that same binary blob of workload is able to function in the same way across both of those environments so that it can be tested in the cloud and deployed to the edge node. If we bring all of these things into the cloud native space, this is how we envisage the move towards the software-defined vehicle. Okay, but as I've kind of expressed already, there are two different worlds. Okay, infrastructure has relied on the OCI standards that exist today around and CNCF standards around storage, networking, logging, security. They have a reliance on mostly a homogeneous architecture. There are other things that are in scope here as well, but the complexity in the automotive space is that we have all of the needs of the infrastructure space, but we add on top the concepts of safety, real-time, heterogeneous compute, and non-functional requirements like intermittent network connectivity and the like. So, what I'd like to do next is introduce a software program that Arm and our partners released recently called SOAFEE. SOAFEE stands for the Scalable Open Architecture for the Embedded Edge. And SOAFEE is the project that aims to address the gaps that I've identified here already, but to do it in collaboration with industry partners and industry experts to deliver that solution into the automotive domain. Okay. So what is SOAFEE? SOAFEE is an initiative to enable cloud-native software experiences across Arm's embedded edge ecosystem. So bringing those cloud-native concepts with all of the additional requirements that were brought into scope for the automotive domain. It's based on open standards. So at the bottom end of the system, we have things like Project Cassini, which includes interfaces like System Ready, which give us a consistent mechanism for booting our solutions, and our rich operating systems, but also things like PSA as well, to give us a consistent means of securing our platforms. So that gives us the basis to securely update, to securely boot, and to bring commercial OSs to the automotive domain. But at the top end, we're looking at the open standards around the cloud native and what needs to be modified in those upstream standards to solve these problems. Again, it's working within the open standards for the cloud native embedded edge. So looking at the OCI specifications for the container runtime and understanding what we need to do in that domain to bring the concepts of mixed critical workload deployment, looking at the orchestrator and understanding what the language we need to use to express the additional runtime requirements we have for these containerized microservices. But SOAFEE will also be introducing an open source reference implementation of the SOAFEE stack. And this is important because it helps seed the ecosystem with a functional platform. Now, this isn't necessarily your functionally safe go-to-market solution as the reference stack. We're working with commercial software partners to implement that functionally safe, commercially supported solution. But what it does enable the tier ones and the OEMs to do is to start investing in software development now for the differentiation that they need in the end solutions. And when they move from the open reference stack to the commercially supported stack, they can take that software with them without having to modify it, without having to recompile it, and without having to reintegrate it. So that's SOAFEE. This is a very complex diagram now, which introduces a lot of concepts at the same time. I'll do my best to cover it, but there will be other opportunities for us to talk about the SOAFEE architecture as time goes on. Okay, so at the bottom end of the stack, we have the compute nodes, the physical systems that we're running on. And this comprises of, like I've said before, heterogeneous compute nodes. So we've got CPUs, and those can be real-time microcontrollers, application processors. We have GPUs for rendering. We have accelerators and NPUs for ML workloads and GPU style of workloads. We also have safety CPUs, and these will be hard real-time capable locked cores that are running in locked mode so that we can achieve those ASIL-D requirements from a system perspective. How we boot on top of these is covered by the system ready requirements. And SOAFEE will be working within the system ready domain to express additional requirements in terms of these software expectations to hit the runtime requirements of the workloads that we're going to be running. So there may be extensions that are recommended into the system ready space as a part of what we're doing within the open collaborative SOAFEE forum. As we move up the stack, we move into a standard system ready firmware with safety and real-time extensions. So this adds again those deltas that we need for the functionally safe environments that we work in. A little bit further up the stack, then we move into the hypervisor. Now, the hypervisor is hugely important to the architecture that we're delivering because it gives us a control point for controlling and managing the separation of compute entities within the system. It also gives us the ability to control the microarchitectural components of the system in a consistent way. So the hypervisor here will work very closely with the orchestrator. So the orchestrator will be in overall control of what gets deployed on the system. But the orchestrator, through the extensions we're adding through the upstream standards bodies, will be able to express the runtime requirements of the services that we are now going to be deploying. So the orchestrator explains to the hypervisor what kind of environment we need, how it needs to be configured, what I/O devices it needs access to, what the real-time constraints are. All of this goodness comes together to help control and configure that underlying system. we also contain, have the container runtime here in scope. Now, because the OCI container runtime specification is a standard, there are multiple different implementations of this container runtime. The vanilla version being the runc that the OCI gives you as that reference implementation, and that's used by many containerized solutions such as Docker today. But there are many others as well, and they are developed based on the runtime requirements of your end system. So it can be based around safety or security or low memory footprint or speed of booting. There's a number of different aspects that can come in scope. So through SOAFEE, we will be selecting the correct container runtimes based on the requirements of the services that we're going to be ending up running. We now move through to the actual services that we're going to be running here, and we're showing that we have different runtime environments for these services, be it a Linux-based or an RTOS-based solution. These are controlled by the hypervisor and deployed to the system. But within this dotted line here, we actually have our containerized service. And I'm going to focus on service 1 here. We haven't named what it is or what it does, but I'll explain what it means to the system. So we've expressed through the orchestrator the runtime requirements, the ASOR real-time requirements, the functional safety requirements, all of this stuff to the system, and it's created an execution environment that is fit for purpose for that service. This service is isolated from the physical instantiation of accelerators through technologies like VirtIO. But an interesting point to pull out here is that SOAFEE's opinion is that upstream standards are probably 80–90% fit for purpose for what we're trying to achieve in the automotive domain. What we don't want to do is say a particular standard is not good enough, so we're going to create a new standard. That's the way we create fragmentation in the market, and that's not what we're trying to achieve through SOAFEE. So what we're saying is that with Oasis and the VirtIO standard, SOAFEE will work with them to understand what functional safety and real-time means in the VirtIO space, to work to fix the problems that exist today, so that future versions of the VirtIO specification are suitable for use. So I like to use the term standing on the shoulders of giants. There's a lot of good work that's gone into that VirtIO space already. We want to leverage that good work and move it forwards to the next level that's needed for the automotive domain. And that's the same with all of the standards that we're talking about within the SOAFEE space. Now, the great thing that, because this service here now is containerized and abstracted from the underlying system, it means that we can move this seamlessly between, up here we have a representation of the cloud or into the vehicle. So we can start to see how this service can start its life in the cloud. It can be executed in the cloud. It can be tested, validated, and remodeled in the cloud before being moved into to the end compute node. We'll have another example of that later in the presentation. I'm going to cover the safety island quickly because it's an important aspect of what we need to do in a functionally safe world is to monitor the health of services that have higher levels of safety requirements. And so ARM are working to produce a standard interface for communicating between these services and the safety island. And SOAFEE will include a reference implementation of that. And again, it's a reference implementation. It's not your go-to-market solution, but we're working with commercial software vendors again to produce your functionally safe equivalent of that service, meaning that this service 1 here, it can be developed on the reference architecture and developed with a commercial and OSV's implementation. Okay, so we've covered SOAFEE, a high-level overview of the SOAFEE architecture, but we need to go into some of the value propositions of why this is good, why it's going to improve our overall software quality offering in the automotive domain. And one of those things is a part that DevOps is around the tooling. So again, fairly complex diagram, but what we're showing here is the standard DevOps workflow exploded out. So we've got the plan, the code, the build, test, release, deploy, and monitor. We're going to explode the test module here a little bit. Because what SOAFEE enables us to do is, in the early days of software development, what you do is you'd integrate everything, you take it to the lab infrastructure, and you test the system in its entirety. And this would be this module here. Okay, so we'd have lab infrastructure set up, and we'd test that on real physical hardware. But what SOAFEE enables us to do is on the right-hand side over here, is use technologies like ARM's fixed virtual platforms, which are virtual implementations of future ARM architecture, but run that in the cloud. And the great thing about this is it enables us to test and validate software before deployment to real hardware. So we start to see how we can accelerate that move towards the adoption of software before hardware is available, so shortening that time to market. But what we can also do is we can do validation within the cloud as well. So we can start to use tools like ARM's Gator daemon to extract runtime information from the workloads. And then you start to put developers in the loop who would do the analysis of the virtual platform operation, so we can have a good level of confidence that it's going to do actually what we want to. So the developer will flag good or bad in terms of the release, and then we go back through that cycle of developing, again, refactoring and testing until we're ready to approve. So that's how we start to do validation in the cloud. So very quickly, a couple of use cases. So we're working with the Autoware Foundation on a project called OpenAD Kit, which is a project that's taking the Autoware offering and doing that microservices segmentation of the end solution. So SOAFEE as the software architecture is enabling this. But we're also introducing at Dev Summit the Ava development platform from AD-Link that is our preferred platform for autonomous development. I'm not going to talk about that platform now, but this gives us a good functional platform for automotive development. There are other presentations today that you can see to get more information on that. OpenAD Kit then works with the Autoware, with the segmented solution. We use the orchestrator to pull that functionality down. So with a single command line, using the SOAFEE platform on the Ava development platform, we can have a fully functional autonomous drive solution operational. We're currently working with tier ones, OEMs, and autonomous drive companies through the Autoware Foundation to make this a possibility. And then there's value to all of these guys because it enables them to do early validation and shorten their go-to-market time on technologies around Autoware. But because of the microservices-based solutions in Autoware as well, it enables us to drop in commercial replacements for the open Autoware reference implementations for some of those. So it enables us to explore go-to-market solutions. We are working with OSVs and ISVs to do the software validation and integration, and also universities who are part of the ecosystem enablement of the whole solution. Intelligent workload migration is another interesting use case where we have these microservices based, and we're looking at a simple object recognition and doing an action based on recognized objects workflow here. So we've done a microservices based solution here. We've got a module that does object detection, a module that does object recognition, and one that does the actions on the recognized objects. But on the SOAFEE-based platform, on a feature-rich SoC, we can do all of this in situ. But when we move to, if you wanted to have a cost-controlled solution that wasn't as feature-rich as my Ava desktop development platform, but we wanted to go into a smaller, cheaper solution like the one here on the right, what SOAFEE enables us to do is to use the exact same workloads that are deployed here on the left and migrate the object recognition, which is by far the most computationally intense part of the problem, into the cloud. So we do the object detection on device. We then just send the information about the detected objects to the cloud. So we're reducing the backhaul bandwidth. We do the object recognition in the cloud and then send that, the recognized information back to the edge device to implement actions on that data. So, the conclusion. Right? The move to cloud native is happening in areas outside of infrastructure. Arm and our partners are working together to solve domain-specific issues that exist in adopting those cloud-native methodologies. And through the adoption of those methodologies, we're going to create a better, all the buzzwords at the bottom, a more secure, quicker to market, safer, easier to maintain, higher quality, software-defined future for all of our edge devices. So thank you very much. My name was Matt Spencer. As I said, if you have any questions, please reach out to me. My details are in my bio. Thank you very much.